forest operation at the University of Padua, Italy. And I'm here also as an officer of the IUFRO. I'm responsible for the research group 301, that is Harvesting and Transportation Engineering. And I have also the office to spend a few words about IUFRO. So IUFRO is a global, not-profit, not governmental, and not discriminatory organization established in 1892 with headquarters in Vienna, Austria.
Welcome from my side. My name is Janine, and I'm working at the Swiss Federal Institute for Forest, Snow and Landscape Research. And I have the great pleasure today to moderate this session together with Raffaele, Cavalli, and with Angelo. And also next week, there will be a second webinar. But now we do not want to lose more time. So let's welcome our first speaker, Henri Riihimaki. He works as Chief Operating Officer at Prefor. And Henri's background is in academia, where he gained expertise in remote sensing, machine learning, environmental modeling, and forestry. And before Prefor, Henri has worked as a researcher in the Finnish Forest Research Institute and as a doctoral researcher at the University of Helsinki. He's passionate about developing better solutions for managing Earth's forests. And we are very keen to listen to your presentation, Henri, which is about the benefits of precision forest inventory. So thanks a lot for joining us today. And the floor is yours. You have 20 minutes.
Okay, thank you very much, Janine, for the introduction. And first of all, invitation to be here. It's an honor to be here, and really excited to tell a bit more about our company and what we do in the field of digitalization in forestry. So I will share my screen.
Perfect.
All right. Good. So, as Janine mentioned, I'm Henri, and I'm working as a Chief Operating Officer at Prefor. Previously, the company was known as Silver, but recently we dropped the Silver brand and switched to use only our legal name, which has always been Prefor. The company has been founded in 2017, and we are based in Helsinki, Finland. We are privately owned here in Finland as well, and currently we have 14 employees, including foresters, data scientists, robot engineers, software developers, and drone pilots. And I think it should be worth to mention now that we have a global audience that I will be mainly talking from the point of Nordic forestry. So please excuse me for that. What we do basically precision forestry services, and our core products at the moment are precision forest inventory, which basically means individual tree level information about trees, and that information aggregated into compartment level data or tile level data or whatever data level is basically desired at any point. Based on this precision forest inventory, we also produce precision forest management plans. So when to do next actions and what kind of actions should be done. And in addition, we are developing new solutions for precision forestry logging operations, including the logging machines themselves. So we have a large development project ongoing. There's a lot of academic collaboration as well. It's a part of EU-funded DigiForest project. But overall, the goal is to develop a fully automatized machine, which can be then used in logging missions, which are basically planned based on the precision forest inventory that we also produce. So we kind of aim to work from the mapping to actual logging operations. So the whole forestry front, basically. fourth point that we are actually offering is related to forest property valuation. So when we have a precise forest inventory at hand and we know how much saw log or fiber logs we have, we know the value of the wood and the value of the bare land, we can then accurately value the forest properties. So this is one product that we are developing at the moment for the Finnish market. And fifth point is related to customized precision forestry analysis. So basically in this case, anything that's related to individual tree level mapping and for example, some sort of monitoring solutions could be mentioned here. I think it's worth to mention also or discuss the differences between traditional forestry operations and precision forestry. And on the next slide, I have a few bullet points how I basically see it. So what makes us or our solution different from others is that or traditional maybe service offerings is that we use latest mapping technology and we produce wall-to-wall measurements at individual tree level, covering the whole forest property. So there's no sampling involved in anything in comparison to like traditional manned operations, which are basically based on some sort of sampling designs. We also do on-demand mapping, so when it's needed, and based on this mapping data, we will then do data-driven decision making or assist in a data-driven manner in that decision making through our product offering. The data is also really precise and available from the individual tree level, so we know how the trees are located within stands, and there is no aggregation really involved in the visualization of the data. So we can really see the finest level of the forest based on our mapping product. So these are the key differences that I see, which makes us different from current other providers in the market. So how do we basically do this? Well, we mainly utilize drone-based data collection. You can see one of our drones on the top right corner and our pilot operating that drone. And drone is used basically everywhere we do mapping, and if we know that there are some problematic areas where the forest stands are really dense or multi-structured, then we might complement the data collection with backpack scanning. We have a separate presentation about that later on in the webinar, so Maurice will talk more about backpack scanning, but that's also a technology that we are using to basically produce the data that we need for the further analysis. The mapping areas that we typically do are around 20 to 400 hectares here in Finland, and I would say that the median property size is closer to let's say 50 to 60 hectares than 400 hectares. So they are relatively compact in a way. Main output from these mapping operations is either way a very high resolution point cloud. You can see example on the right side of the slide. And that point cloud is then further analyzed and processed through a fully automated cloud-based processing pipeline where we get the individual tree level forest inventory as an output. And in addition to that, we also get the compartments and the data aggregated into the compartments and management actions for these compartments. And all of this is visible through our user interface where the data can be viewed and also downloaded. So basically the customer is using our user interface where he can see everything and then download desired data formats from there. So what are the benefits related to this individual tree level information? Well, the way I see it, it really reveals the required detail we need in forestry. And we can see that from this image that we have on the middle, that if we go from compartment level to tile level and then further to trees, we see that the map representation is really different. So with the individual tree level data, we can see that the trees are clustered, and in parts of the compartment we have empty areas, and many other crucial details which can, for example, help in the planning of logging operations. So I truly think that this is really useful information, and it also gives us the opportunity to use any kind of geometry that we desire. So there's no limitation in that sense. And we have also developed a tool for that. So here you can see our user interface and example about the tool that we have developed. So here you can see a compartment. The dark lines are the boundaries for a compartment, and let's say that the user is interested in some specific area inside that forest and wants to check what kind of wood he has there. So by using our map functionality, the user can check in real time any given area and the tree size distributions here. So you can see that the histograms, which are showing the diameter distribution and the height distributions, they are automatically updated by the geometry that the user is giving to the user interface. And that's the whole point, really. So this individual tree level data can be aggregated to any geometrical unit that we want to use in decision making. And that's really the key benefit out of this. Then clear benefit that we can also get is the increased accuracy. So by using this kind of high precision mapping, we are able to reduce errors in comparison to traditional methods. Our internal aim is to be below 5% error in compartment level in the key metrics, which include trunk count, volume, and basal area. And species detection accuracy for the Finnish use case is also 95%. So 5% error margin there. Luckily for us, Finland is kind of nice area to test this because we have only 3 or 4 main tree species here, but in that way it's good for us. And yeah, we are just finalizing the evaluation of the inventory accuracy, and it's looking quite good. We are really close to this 5% error margin at the moment based on the latest internal data. So when we have this accurate data, that then basically enables better decision making and using this data-driven approach. So when we know that the key metrics which we use to make the decisions are correct, we are able to time the forest management and logging operations much more precisely than using data which is outdated or not precise. In a similar manner, the valuation of the stand or forest property will be accurate as well. So we get economic benefits as well. Next point I have is related to shared reality. So basically, when we have this really accurate point cloud as a basis, it can act as a digital twin, which can then be used for stakeholder communication. So we can use this point cloud to communicate related matters between different stakeholders. For example, forest owner might want to tell a logging operator that there is some specific area that should not be cut, and this area can then be viewed through the digital twin. which is accessible throughout the mapped forest property. So this is another clear benefit that I can see from this kind of really accurate and close to reality data. Forest monitoring is of course important as well. So we have the individual tree level already from a single scan, but if we do multi-temporal scans, so let's say that we have a disturbance event like an insect outbreak or storm damage, we can then do a second scanning and see which trees or which areas were affected. And we can get a really clear, precise picture about that as well. And actually we have ongoing customer project in Germany, near Leipzig, where we did kind of first data point for monitoring ash dieback. So when we perhaps do a second campaign there, maybe 2-3 years from now, we can maybe see which new trees were or died, and then we can see which areas were affected and how fast the disease is spreading. And regular interval monitoring, let's say every 3 or 5 years, could be used to monitor forest growth, productivity, and carbon sequestration as well. So that's also one interesting application and benefit we get out of this. Ultimately, we of course want to have economic benefits as well. So if you are buying or selling wood, having the accurate data as a basis decision-making tool, that's really beneficial as well. As I already mentioned, we can optimize forest management, time the actions correctly, and this way increase the yield we get out of the forest. And as also mentioned, I clearly see that this is a tool for better planning of management and also logging operations. So I think using this information we can save costs. There's not so many needs for doing site visits as the forest can be visited also virtually. So that's a clear benefit as well. And lastly, as mentioned, carbon crediting could be a thing of the future as well. So somehow validating that carbon sequestration becomes more and more important. So precision forestry is a tool for that as well. Environmental benefits, they come from multiple sources, but for example, detecting the forest structures, tree size distributions is really important for biodiversity. So keeping the structures as heterogeneous as possible, then we are creating better habitats for multiple species, and this way increasing biodiversity in the forest. We can go even further and use individual tree level detection of biodiversity, so detecting highly valuable individuals like large aspens here in Finland. That could be done based on this data as well. And locating also habitats like vicinity of streams or areas close to rocks or large rocks which have kind of a unique microclimate. This data would be usable for that as well. And last item on the list, as I mentioned earlier, we are developing automated logging solutions. So the precision forest information is kind of a prerequisite for this kind of work. And when we have the accurate a priori information about the forest stand, we can use that for planning automated forestry missions. And we basically know which tree we need to cut and from which point. And using this information, we can create mission plans, which can then be automated. And right now we have started developing this supervised automated harvester, aka SAHA platform, which is about to do just just that. And this is basically a collaborative project where there is a strong academic collaboration ongoing as a part of the EU DigiForest project. Currently, we have 2 sensor testing platforms named SAHA-1 and SAHA-2. One of them is in Switzerland and one here in Finland. And in addition, we are also developing a completely new model called SAHA-3 at this point, which is not based on any earlier design, but it's completely new product designed for this particular use case. And that's it from my part. Thank you very much for your attention.
Thank you very much, Henri, for a very interesting overview about your research and for sharing your work and your tools. There have been some questions in the chat, and one colleague was wondering on the tree level, how well can you distinguish different tree species in the mixed even canopy stands?
Well, in Finland, it's above 90% in most of the cases, depending on the situation, quite a lot. So, but overall, I would say it's between or around like 92, 95%.
And this leads directly to the next question, which was how many tree species can you detect? And do you have more information for the individual tree, like the volume, the dimension, any other thing, maybe aspects related to biodiversity, which I think you mentioned already, but maybe you can give some more insights.
Yeah, so the basic attributes that we have for trees is tree height, crown width, starting point of the canopy, so basically the height of the first living branch, tree diameter at breast height, sawlog volume, fiber volume, energy wood volume, and the total volume of the tree as well. We don't have any biodiversity values yet at the individual tree level, but we have ongoing project. It's the same project I mentioned in Germany, where we are developing algorithms for detecting that. Don't know the outcome yet, but that's something that we are actively working on, and hopefully we can release some features about that in the near future as well.
Yes, and I also put the link to the DigiForest project into the chat, and there are coming more and more questions, and I assume, Henri, you will stay with us, and if there are more questions, you can also answer them directly. Maybe one last question was whether the harvester will be connected with the stand 4D. I think it will be the case at the end. Isn't that planned? Or maybe we can leave this question also to Maurice later.
Yeah, I think we can leave it for later. All right.
Yeah. So, but maybe for also the stand 4D as a standard data format in a harvesting machine. And I think the moment where the machine will be commercial, it should work with the stand 4D. And I think this is, at the end, this is the aim. If we have a digital workflow, the data need to be communicated to the harvester and from the harvester to the forwarder and so on. So the aim is to have a full digital workflow. And for everything, please.
Yeah, and overall, yeah, we aim to follow all the standards. For example, the forest data that we distribute, it's following the finished forest standard. So having standards is good. That's
good, exactly. So with this, Henri, I would like to thank you again very much for your nice presentation, and for all the others, you can continue asking questions in the chat, and Henri and also the other speakers will be with us. So thank you, Henri. Thanks. And now we move from Finland still to the Nordics, and we come to Sweden to welcome Pedro La Hera. Pedro is an associate professor at the Department of Forest Technology at the Swedish University of Agricultural Science, SLU, and with a PhD in applied physics and electronics from the University of UMU, his research focused on developing cutting-edge robotics and control technologies to advance heavy-duty machine automation. His work includes tackling challenging problems, such as the developing control technologies that allow forced machines to work autonomously with the need for human supervision. Dr. La Hera's expertise lies in control algorithm, sensor signal processing, artificial intelligence, computer vision, and motion planning, which are all vital areas in the field of robotic research. And it's a great pleasure to welcome you, Pedro, and the floor is yours, and we are very excited to learn about your presentation about machine data generation and use in the era of autonomous machines. Thank you.
Thank you. Thank you for the presentation. This presentation has a lot of information, so we'll just start directly talking about it. But as you mentioned, I have a background in robotics, and I've been working with automation for about 2 decades. So as many people of you might know, on autumn of 2021, our research group presented what would be known as the first fully autonomous forwarding machine. And this machine is being developed in between different teams here in Sweden, from which we are part of the development. So what this machine do is whenever you in the computer give the machine a specific area to work, so you give it through GPS data points, you tell it where you want it to move and what kind of work it's going to do. So eventually the machine is capable of fully autonomously drive around this area. And it can do it avoiding obstacles and moving around the trees and so on, using GPS sensors. And it can also observe using cameras and LiDAR. So it has the ability to recognize the logs on the ground that have been left out by the harvester machine. And lastly, it is capable of using its crane or the manipulator to collect the logs from the ground into the trailer, into the machine itself. So all of this is done without any need for human supervision. So it's done fully autonomously. And my part on this project is basically being to develop the crane. So I myself, before working with forestry machines, I used to work developing control algorithms for different robots. So for example, industrial robots in different countries, as well as different control algorithms for more complicated systems that we are interested in developing in the robotics community. But when I moved to Sweden, I became, or I'm quite known here in Sweden because I've been developing automation technology for hydraulic machines, and specifically forestry machines. And over the years, I started a lot of different projects that ended up being products that we can see today in the market from some of the most well-known companies out there, like Komatsu Forest, John Deere, and so on. So it's a lot of development that has resulted into products. So the development of the machine that I presented at the beginning, we call it the IUFRO machine. It's not something that is being done just in a couple of years. So this is result of decades of work. And basically in this presentation, I'm gonna walk you through the development of the automation for the crane. So as most of you know, forestry machines are basically operated through hydraulic technology. So they have cylinders, they have pumps and so on. But there is a problem with most of the machines today. And the problem is that most machines, they don't really have real sensors. And by real, I mean sensors that you can use for automation. They have some sort of sensors, but they usually cannot be used for automation. So, and the second problem that you get with them is that they have no real computers because they are usually manually operated machines. You don't need so much advanced software, advanced computers to be able to operate them. So there is a lack of technology in these machines. And the problem with that is that, you know, by nature, most of these machines or most of these cranes, they are usually have this very bouncy behavior, which you can observe when you are driving the machine yourself. So usually there will be a lot of oscillations, vibrations on the machine itself. And that can actually provoke that whenever you are trying to really do precise movement with these vehicles, you might not be fully able to do it unless you are an expert. And one of the main reasons is that hydraulic hasn't really been developed as a method to fully actuate these kind of systems. Originally, hydraulics were developed as suspension systems. So the technology to be able to move heavy loads is kind of not too advanced in the hydraulic industry. So one of the challenges that I worked, well, kind of for the last 2 decades, is to transform this into these very uncontrollable oscillatory systems into something that can be controlled just like a robot. And everything starts by introducing sensors on the machine. So on these machines, for example, over the last decade, specifically the year 2013, the company Eaton released the first version of a fully sensorized valve, which means that this valve is not only capable of producing pressure and forces, what it actually can do is measure everything that is going on in it. So it can measure pressure, it can measure flow, electrical lines, and all of that. So we were working with this company for kind of a long time before they released this product. And the research that went behind it were specifically to transform this kind of like oscillatory behavior on machines to something that becomes a lot nicer to control. So the machine itself, once you start programming them using sensors, then you can eventually start controlling these machines more accurately, pretty much like the way robots work today. So kind of these are experiments that were done almost 15, 16 years ago. And some of the most recent experiments just a decade ago could transform these very small, non-sophisticated machines that have this kind of very wavy behavior into something that becomes a lot simpler to control. And this helps a lot the machine operator because it doesn't provoke that the machine needs to be oscillating all the time, and then it becomes nicer and more precise to do the work with the crane. So all this development was transported to the Aura machine. So originally you can see here the crane working, and without any form of software, this crane or this machine itself would be very oscillatory and it would vibrate a lot, which is not something that you want to have when there is not a person in there, because the whole machine can tilt over. But the machine itself, it has a lot of sensors. So the valve is a very complex valve, and it has sensors for measuring the flow, the pressure, and most of the stuff that we are doing with it. So using the technology that we had before, well, improvements of that technology, we could transform that kind of very heavy oscillatory movement into very precise control, as you can see there. So on the left, you can see like the oscillations and so when no control is being applied. And on the right side, you can see a machine learning algorithm that knows that this should not be happening. And so this becomes also important for the crane itself when it's moving. So in this point that you see the crane doing very fast movement, and here you see when it's not controlling it. So in this case, the machine has the ability to learn that there is something that is provoking this kind of very distorted oscillations, and it starts learning that it needs to start moving differently to the point that no oscillation is gonna happen. So this part would be the first part in which you can start taking hydraulic technology into something that becomes simpler for control system people and for people in robotics. So it becomes more suitable for them to be able to use in automation. So based on this kind of developments over specifically the year 2015, one of our companies in Sweden started launching the first forestry cranes that had fully embedded sensors in the joints. And what this allows you to do is to measure every single position in which the machine is moving. So it allows you to measure movement. And by measuring movement, you start transforming this crane into something that has eyes, pretty much like a human. So I will show you some examples that was done very, very long ago, in which, for example, you want a crane to move in a very specific path. And by using the positions, the sensors, you can develop a control algorithm that is capable of doing so. So you can plan something and then the crane itself can do it on its own, as you can see there. So these experiments were done about 20 years ago in a laboratory setup. And some other examples for in the same setup was the ability to just pick point wherever you want the crane to move, and the crane will just, well, magically start going to wherever you want it. And this is a technology that exists today in the market after 20 years of development, and is known as the intelligent boom control in the case of John Deere, the smart crane control in the case of Komatsu Forest. And there is a lot of companies selling similar development today. So now the way we develop these algorithms has changed a lot. So instead of using this kind of big laboratory equipment, we just 3D print a lot of the development that we're doing. So in this image, you can see a 3D printed version of a crane, or kind of similar crane that we're using in the Oro machine. And what we do is to just program in it. So this crane is equipped with all the sensing technology that is almost equal to the crane itself. And we can do pretty much the same experiments with more advanced control algorithms, as for example, the ability to move the crane specifically the way you want it. So very accurately move as you decide. And eventually this kind of accurate position control is something that we have programmed in the Oro machine itself, because the Oro machine is one of these crank cranes that has all the sensing equipment in it. And based on these sensors, we can develop control algorithms that can actually make it move the way we want. So now from this point forward, you need to think that if you can smoothly control this machine and you can make it move the way you want it, so then the next question that you gotta answer is, so now how do you want it to move if you are in the forest? So because the machine has sensors, or well, we implement sensors on some machines, about 10 years ago, we had the idea of recording how people are working. So here in this example, you are seeing the data of a person that is being working in the forest with the crane. And because we have sensors on these cranes, we have the ability to record everything that is going on from his hands, from the control of his hands. And that gives you an indication of how the people are actually working. And And because you have data, eventually what you can easily do is to use control a machine learning algorithm that afterwards, after learning from the person, starts doing the whole job on its own. So you can see it in this case that now the machine has learned from the person and is starting to develop. The machine now is deciding everything on its own. So all of these kind of controllers. Now you got the control algorithm, you have the pressure controller, you have smooth movement, and now you have an ability for the machine to move in the way it wants, in the way you need. So basically combining all of this is what we have in our machine, so that the crane can start doing work on its own. So in this particular example, that is a video that you can see in YouTube, the complete video. After the machine is being able to detect that there is a log to be collected, it has the ability that on its own, it can go grab it and bring it to the trailer, just the way we program it to do. So all this kind of development is something that is being going on in the Auro platform, but the Auro platform has much more than that. So it has the ability to autonomously navigate. It has the ability to observe the terrain. It can observe there is recognized trees around. It can drive on its own. But that is development that I'm planning to present in another occasion, because as you see, every part of this development, it's kind of pretty long. It's not something that is being done in just a couple of months. It has history. And the development of autonomous navigation, the development of tree recognition, the computer vision, each one of them has its own challenges. So that's everything that I have prepared for you. So thank you for the attention, and if you have any questions, I'm pleased to answer.
Thank you very much, Pedro. It was quite impressive to learn about the history of development, what you just mentioned and showed to us, and also to see how your lab is equipped. That's quite impressive. Thanks a lot. So I think I did not yet see if there are any questions directly in the chat, but I think you will stay with us also for the next half hour. So feel free to ask your questions into the chat, and Pedro and also Ola, they are here and can answer your questions.
So thank you for myself. Bye.
Yes, thanks, Pedro. I was just waiting and see if there's another question, but not right at the moment. But I think many questions will come up. Maybe we can just, Pedro, if you're still there, can take over the question from Henri asking what was the simulation environment used in the demo?
Well, that's a question that a lot of people ask, but in reality, I never work with simulation because I don't believe it. I've been working with robotics for a very long time, and I see how simulation just usually fails. So what I like to do is to always develop stuff that can work on the real system. So that's why a lot of my development is directly implemented on small machines, big machines, testing platforms, because that's the only way in which you can know if that is true or not. In the last slides, what I presented is just a visualization of what the operator did. In reality, we recorded the data in a machine in the forest with real operators, and you are only seeing a recording of what happened really when it was moving. So there was nobody moving anything on a simulation environment. It was not like that. It's data coming directly from the operators.
Okay, thanks for clarifying.
Yes, thank you, Pedro. Oh, it's really impressive. So before we come to the next speaker, to Maurice, I would like to use the opportunity to announce a special issue from the International Journal of Forest Engineering. I think Angelo just posted the link into the chat. So Angelo and I, we have the honor to act as a guest editor in the International Journal of Forest Engineering, and we have set up a special issue about digitalization of forest operations. And to summarize, the core question that is addressed in this special issue is how digital automation and IT-based applications can be used and made applicable to benefit the wood supply chain. And the deadline for submissions is by the end of August, and we like to use this opportunity to draw your attention to this special issue. And if you have any questions, please do not hesitate to contact Angelo or myself. Or also, I noticed the editor-in-chief of the International Journal of Forest Engineering is with us as well, Charlie Blin. So just put questions into the chat in case you have some, or you can also contact us afterwards, so in the next weeks and months. Now I would like to present the third speaker to you, Maurice Fallon. So let's move to England. Maurice is an associate professor and a Royal Society University Research Fellow at the University of Oxford. And his research is focused on probabilistic methods for localization and mapping. He has also made research contributions to navigation, to state estimation, and 3D mapping for ledged robots. His PhD was from the University of Cambridge in the field of sequential Monte Carlo methods. He worked as a postdoc in Professor John Leonard's Marine Robotics Group in MIT from 2008, before leading the perception part of the MIT's entry in the DARPA Robotics Challenge. He has worked in domains as diverse as marine robotic detecting mines, humanoid robotics, and mapping radiation in nuclear facilities and forests. So Maurice, we are very happy that you are with us, and you brought a presentation about using walking robots and drones to build accurate 3D forest models. So the floor is yours.
Okay. Janine, can you see the presentation and hear me okay?
Yes, perfect.
Okay, so thank you very much for the invitation today. And I'm going to use it as an opportunity to introduce the DigiForest project, which Henri has mentioned before this, and to go into a little bit of detail about the initial progress of the project. So DigiForest is a 3.5-year European-funded, Horizon Europe-funded project looking at improving or developing technology to digitize and to improve informed forest management decision making. And it is kind of a large variety of different systems being developed by a variety of different collaborators across Europe, and we have a variety of different strands to it, some of which Henri has mentioned. But there are 4 kind of major ambitions. One is to create autonomous robotic systems, both legged and aerial drones, both above and below canopy, that do mapping and reconstruction down to individual tree level, as Henri talked about, and to feed those different sensor sources through to decision support systems. Maybe different robotic platforms are more practical for this at this stage, but we're developing a variety of different technologies in parallel. For example, above canopy drones are more likely to be commercially practical, given the number of hectares they can cover, but within the aims of the project, it's quite broad. And then finally, feeding into the harvester, which I won't talk about very much today, but Henri alluded to a little bit. I'll mostly talk about the first 2 aspects today. This is an illustration of the different robotic platforms that we'll be using in the project. Drones from 3 of the different partners, including this integrated drone that's been developed by Leica, and a much more focused aerial platform. Actually, I don't think this is the preferred platform from Pre4, but it was one that was used in a recent trial. This legged robot that I'll talk a little bit about a bit later, and a custom designed drone developed by partners in Norway, NTNU Norway, and co-developed now TU Munich. We also do a lot of work with backpack portable mapping, so as to ease the data collection aspects to start to build out sensor fusion aspects. The project's goal is to improve digitization and to feed the map reconstructions that were true into subsequent post-processing operations to do the kind of species classification. And there's a specific focus on the robots being lightweight and minimal, and the harvester itself being sustainable, perhaps with a focus towards continuous coverage operations. And so now I'm going to shift to talk a little bit about the 3D mapping technology that we developed. I'm a roboticist from background, and I'll talk in some technical detail about the methods we use. And you can see here an illustration of an earlier version of our backpack device on the left-hand side, and the legged robot Animal, which is developed by a Swiss company called Anibotics that we're using in the project, and the variety of different sensors that are on board. Typically, the workhorse for LiDAR scanning is a laser that you can see on top of the handheld device here, but we're also capturing multi-view camera, for example, to do species classification, and also to generally create a richer mapping environment. And a key sensor that's at the heart of the device is inertial measurement units inside of the device that are key for measuring high frequency motion. The legged robot augments that with sensors for mapping the ground, green and white, and also the red joint sensing. And a piece of technology we've had is to build up infrastructure for earlier versions of this legged robot to combine together its onboard joint sensing and its vision to track its motion very accurately. So this blue line is estimated from the onboard vision and leg sensing, and the green is from ground truth from a tracking system, solving an optimal estimate of the trajectory of the robot as a series of least squares optimizations, and I won't go into great detail about that, but we've since incorporated into that LiDAR, tracking partial features of different blocks of the LiDAR, for example, planes or tree edges, and that all becomes extra constraints in a factor graph that's made up of information from the IMU, planes detected in the laser, edges from for example, door jambs or walls, or lampposts or individual trees, and then visual points that from the camera systems, all solved in a windowed optimization. And switching to handheld systems, this is an illustration of both the data collection process, illustrating that it's quite minimal and also able to deal with quite aggressive motions. On the right-hand side, you can see a visualization of the density of reconstruction with an early version of our handheld prototype. Here you can see with a view to construction, because that's a key application area for this type of technology, is a centimeter accurate. So it's been quantified with terrestrial or TLS from Regal scanners, to within 1 centimeter of the TLS reconstruction from a handheld sensor that can be captured in a matter of minutes, as opposed to maybe a full day, and very inconveniently so for TLS scanning. So with a view to the DigiForest project, we've been adapting that system, incorporating it within a backpack, and making quite a minimal system that allows us to at scale collect reconstructions. And that's driven by the fact that while it's the gold standard of reconstruction to use high accuracy TLS scanners, it's particularly laborious, and as Henri mentioned, it's not possible to do what you would call wall-to-wall scanning, where you scan the entire environment. You're typically limited to 30 by 30 meter plots and the need to extrapolate from that. So with mobile scanning, we can achieve the speed at which a person can walk, which is in the order of 2 to 4 hectares per hour. We also don't heavily rely on GPS. There is a GPS sensor attached to our payload, as you can see on the top right. This is a GPS antenna. We don't use RTK because it's quite difficult to get reception in remote locations. So using minimal GPS information can give you this red line that you see. So that in this particular mission, the backpack started in the bottom right and went around the boundary of a plot on the access road before entering. And you can see that the red line corresponding to GPS is really very inaccurate. So it's affected by dense coverage in the canopy. So really we rely on the onboard sensors, the IMU, the vision system and the LiDAR to track the motion of the device, and then use GPS primarily to indicate where in the environment it is. We want to do more with that by going to use lower level constraints from the GPS, so fusing partial observations over time. But at the moment, the bulk of the work is done with vision and LiDAR. And here's an illustration of the system running live. The map is being generated on the handheld device being carried by one of our researchers, going through the woodland, and you get a feel for what that's like to do on a daily basis, particularly in May and June, when in Oxford anyway, foliage is at its highest. But this visualization here has been transmitted by Wi-Fi back to this tablet, and in typical operations, the operator would actually hold the tablet to be able to make sure that they can achieve full coverage, don't miss any patches, and achieve complete coverage. Then building upon that, we can do things like mapping the terrain. So this is extracting the terrain and filtering away the trees to give information, for example, about maybe drainage patterns or the most appropriate ways for harvesters to approach a particular stand, extract individual trees, and as we go through the EU project, implement more of the species classification and quality evaluation that Henri was talking about earlier. This is an illustration of individual tree diameters, locations, and principal axes. We're also scaling this up, so you can see here an illustrative map of as much as 5 kilometers of walking being combined together into a single consistent map, where GPS is only used to situate the map within the world, but not to actually influence its shape or reconstruction. Now I'm going to shift to talk about a different topic that I'd imagine is quite different to what you would have in this particular type of workshop. Another strand of the work is to incorporate legged robotic systems. So this is an animal robot developed by Anibotics, and as you can see from this very short clip, the robot is capable of walking in quite complicated terrains, typically terrains in which the environment doesn't contain natural growth. So the work from the ETH group in particular has developed reinforcement learning-based locomotion control that allows the robot to have a very reactive ability to recover itself when walking in rough trip hazards, like you can see in this illustration, but really struggles when you move into environments like this. It's using the cameras around its body to determine where the terrain is, where it should plan to place its feet. So soft growth like this, where the robot can definitely pass through, actually kind of confuses the robot and fools it into thinking that this environment is not traversable. This is what the robot's eye view is, and it wouldn't be able to plan its route through that. So an initial piece of work within the frame of the DigiForest project is looking at how we can use visual information, which is notoriously difficult to work with typically in the wild, as a training signal when a human is first tasked with teleoperating the robot for a few minutes in an environment. We can learn where the robot can safely walk, and as you see in this video, eventually after just a few minutes of teleoperation and a few loops, the robot is now able to distinguish between, just purely on a visual basis, between what it can and what it can't walk through. So it's without any manual labeling, without any pre-classification, it's clustering out the segments that correspond to untraversable bushes and trees, by example. This is an illustration of that over the course of a 4-minute training operation. After about 2 or 3 minutes, it's able to determine that. So we're able to bring a robot into an environment where lighting conditions are very evolving or maybe unpredictable. We're not taking advantage of prior training as a result, and we're using this kind of GPU-based supercomputer, mobile supercomputer at Jetson Orin, to do real-time deep learning and deployment on a robot. And we're looking to then use this is illustrative how you can then use it. So having learned visually where the obstacles are, the robot can now be commanded to go autonomously from point to point, and is using the vision to avoid walking into obstacles rather than using geometry, which is the typical approach in robotics. So we're not using LiDAR, for example, here to avoid obstacles, and we're not explicitly building a 3D model. We're avoiding obstacles with vision. Initial work that we hope to further deploy in field trials that Henri is hosting in Finland this summer is to wrap this into an autonomous exploration system. And you can see here some illustrations of kind of lawnmower pattern type mapping, where the robot is broadly following a lawnmower pattern to ensure coverage, but on it, as needed, is deviating to avoid obstacles, large trees that are in its route, for example. So we're gradually working towards building up the fusion of different sensor modalities, georeferencing them, and bringing them into usable user interfaces. So that research that Janine and Henri are working on to provide this kind of information to allow decisions to be made. This is an illustration on the bottom right from Pre4's commercial product. I'll just finish up with to show some more of the laborious work that we're doing to generate references for the accuracy of the reconstructions coming from the robotic system and the different drone platforms. In last month, we had our first field trial for the project, used terrestrial scanning and manual measurement to reconstruct different plots within this cantonal forest in Stein am Rhein in Switzerland. And we have, as you can see here, different sensor types, terrestrial, the backpack monitoring, above canopy, and then we'll augment that with below canopy, as well as legged robot, and evaluating their accuracy relative to the gold standard, which is the TLS. Here you can, that's kind of an irrelevant detail, but thank you for the opportunity for presenting and giving an overview of our project. It's only getting into the first 6 months now, and we're excited about where it will go next. And if you have questions, I'd be quite happy to take them. Thank you very much.
Thanks a lot, Maurice, for this comprehensive overview. Very interesting to see your insights about the different inventory devices that you are using in the project. So are there any direct questions to Maurice? Maybe not yet, but I think you will be with us in the next half an hour. So maybe also for those who came later, just type your questions into the chat, and Maurice or also any of the other attendees can answer the questions.
Okay, thank you.
Perfect. So thanks a lot, Maurice. And in that case, it's a great pleasure for me to welcome our fourth and last speaker for today. It's Arnaldo Gunzi. He has been working on more than 200 projects on advanced analytics, operation research, such as models of forest planning, simulation of the paper supply chain, forest logistics, trim of paper mills, forecasts of volumes and prices, and several others. So he's passionate about the rising field of quantum computing, and his formation includes aeronautics infrastructure engineer, master in EM electronic engineer, MBA in project management, specialization in quantum computing algorithms for cybersecurity, chemistry, and optimization. So this sounds like a very interesting combination, and I'm very happy to welcome you, Arnaldo, and the floor is yours for your presentation about digitalization opportunities and quantum computers.
Thanks a lot for the opportunity, Janine and Angelo. Do you see the screen?
Yes, perfectly.
Okay, thanks. So I'll talk a bit about those topics. But first of all, Klabin, a bit about the company. Klabin is one of the biggest companies in Brazil in paper and cellulose area, with 20 plants. It is a very vertical company in the sense that it has the forest area, paper and cellulose mills, industrial bags, and corrugated packaging mills also. And those are the numbers, some big numbers of the company. The mills are located all along Brazil. Our forest areas are in Paraná and Santa Catarina. Also, our big mills of paper and cellulose are here, also near the forests. And in all Brazil, we have the mills of industrial bags and corrugated paper. I lead here in Brazil, in Klabin, a team of advanced analytics, and the introduction was made already, but our goal is to have a high excellency team, very high level people, to know a very deep about the processes of the company, and also to share the knowledge internally, but also externally. We lead with those topics: data science, optimization, simulation, AI. But my main interest is optimization. We have a lot of linear integer problems in forest area, for optimization of harvesting, logistics, silviculture, biomass, models for long term, short term. So we have a lot of expertise in this field. Also, we are working with a lot of other projects, as mentioned before. I have here two cases to illustrate a bit more, to give a zoom about those projects. The first case is in terms of forest roads. We have here a software. We helped to develop this software to aid the design of roads inside the stand. Here is one example of a stand. We have the lines here are the roads. The blue line represents a gravel road, and the red one is a common road. It is a software that receives this information, the current roads, a digital model of the terrain, some characteristics of the soil, some operational constraints like the maximum declivity that a hauling machine can operate, maximum distances, and so on. We input this in these characteristics in the tool. It calculates for each square meter of the forest, the stand, where is the nearest road, and the hauling distance for each square meter of the terrain to the nearest road. And then it generates a map as this one. It says every volume in the blue area is going to the blue roads. The area in red is going to the red ones, and the yellow area here is infeasible in the sense that it has no solution given the constraints of the problem. Of course, in practice, those small infeasibles are feasible, something like this, because we have constraints like maximum declivity or maximum distance, but you can go a bit more in practice. And it gives some results: the average hauling distance, volume of wood per type of road. And it is very, very important for us in our operations, because Paraná and Santa Catarina are areas that rains a lot. So we have to protect our operation, the wood, the operation of transporting from rain. And for this, we have the gravel roads. So we have to estimate to have a good estimate of these volumes to guarantee the operations. And it also calculates the costs and some other features of the problem. One desire of ours is to reduce the number of roads. Our forestry basis is like 70 years old, So in 70 years, a lot of things change. We have now better machines, more other better machines, a better operation. So we don't have we don't need to have so many roads in our areas. This tool helps to analyze the current configuration of forest roads, and the analyst can say, oh, I don't need anymore this branch of the road, and I can redraw this road to make another road configuration, and then we can run it again and see if the parameters are good or bad, and then we can guarantee that we have operational solution, and then make it operational. We liberated this for the roads construction or maintenance. It is a work that we are working in this for like 11 years. First we needed the digital model of the terrain, a LiDAR flight. Then we developed some initial digitalization of our roads, and then we were ready to implement this software. It is running for 2.5 years, 3 years, about 3 years. And in those 3 years, we estimated that 400 hectares of land, we gained 400 hectares of land that are now productive and in were roads before this study. So it is a very interesting and a problem that it's giving some results now. Another case, a second case that I want to show is about quantum computers. It is not, it's a study. I'll explain here, but a bit about what are quantum computers. The Moore's law is reaching its limit. It's the Moore law is the one that says that each 18 months we have a double of computational capacity at the same costs. But in the last years, it is not so true, and there is a race to get a new paradigms or new solutions. Quantum computing can be one of these new solutions. What's the difference between quantum and classical? In classical computing, we have bits, 0 or 1, that can be implemented using devices as the transistor here. In quantum computing, we have the qubits, quantum bits. It can be described as 0 and 1 also, but also in any superposition of 0 and 1s in a complex plane. It can be like an electron in an atom. The level of the electron can be 0 in one level, 1 in other level, but it can also be in any superposition of these two. Or also a single photon in a polarized, a single photon can be polarized in one direction, and the direction of polarization can represent this qubit. There are two main features, superposition, and the other one is entanglement. You have a correlation between two qubits, and these two are entangled. These are some features that enable some very interesting possibilities of use. Just to give you one example, one simple example, in the classical sense, if I have a black box here in 2 bits, in order to test all possibilities, I will have to test all the 4 possibilities here, 0, 0, 0, 1, 1, 0, and 1, 1, and then calculate using the black box and have the 4 results. In the quantum sense, I can kind of test a superposition of all possibilities. Like I said before, we can make a superposition of them and then manipulate the qubits inside the black box and have one question using one calling to this black box. Of course, it's not so simple as showed here. There are a lot of problems, other problems to consider, like noise and others. But there are some potential applications, mainly this one, cryptography, simulation of chemicals, and combinatorial optimization. These are the most potential applications of this new technology. And what we are doing here in our study is the link of combinatorial optimization, because a lot of forest planning is combinatorial. We are doing a study with a Brazilian university in one partnership to study this one problem. We choose a small silviculture planning problem with just some small, very small, 4 harvesting blocks, 4 blocks, 2 species and 2 months to consider. And the decision is like, what do I plant in each of these blocks, considering 2 species and some other few constraints. It gives around 16 qubits. Commercially, we have at most 400 qubits, just to give an idea of the current states of technology. And the method we are using are fault tolerant methods. This one, KAOA is the one we are trying to test. We are using a language. There is some programming languages, Qiskit, from IBM, that enables you to simulate this kind of algorithms, and also it allows you to run in a real computer in the cloud also. Just to give one example of how this method works, we have the bits here, 0 or 1, encoding the problem we are trying to solve. We have a superposition, we make a superposition of all of them using this Hadamard gate. And then we have a quantum device, a quantum algorithm here that we can manipulate some parameters of this circuit, and then we read the results and see if the result is near or not our desired solution. And then we do it again. It's a hybrid between classic and quantum. There is a quantum part here and a classical optimization outside this box. Our goal here is not to replace our current methods. We have a lot of problems already running using classical solvers, using the top of world solvers like Simplex and Gurobi and so on. We know that it runs every month and it runs very well. But the idea is to explore these new fields of knowledge, understand these opportunities, and who knows, in the future, one solution, one potentially disruptive solution like this can give you a lot better solutions that we have now. So that's our goal. It's a very, very small a test here using quantum computer algorithms. That's what I wanted to share with you. There's 2 cases, one of the forest planning and another one with quantum computers, just a study. Thanks for the opportunity, and here are my contacts.
Thank you very much, Arnaldo, for this interesting presentation. So as you said, this is a very new field of knowledge, and it's like in the upcoming right now with this question of digitalization. So I think all of us will learn much more in the next years about this topic. So thanks a lot. So there was one question from Angelo in the chat asking whether you started using AI on optimization models. Maybe I can add other optimization models available. You are muted, sorry, we cannot hear you yet.
Oh, sorry. Now you can hear.
Yes.
We use a lot of combinatorial optimization solvers here in the forest area, also in industrial area. So we have a lot of models. I didn't understand well the question.
Yeah, that was the question. Maybe you can add the link of your website of the institute or something into the chat as well. So because there's another question referring to all the speakers asking whether these tools, models, and things that have been presented are available and whether they are used actively on the market. And I think it is partially the case. For example, the first speaker, Henri, this is a commercial company, so they are working on this. And yes, of course, this is actively used. And I think the methods Arnaldo just presented, he's using that in his daily work. And maybe the speakers can add some references here into the chat. That would be nice, or maybe some papers or reference projects or links to some tools that would be very helpful. So for the moment, thank you very much, Arnaldo, for this interesting presentation. So if you have some minutes left, maybe you can check in the chat if there's a question referring to you directly. And otherwise, I would also, with regard to the time, would like to use the opportunity to thank again all our 4 speakers of today. I think we have heard very nice presentations, starting with Henri Riihimaki from Finland, giving us some ideas about the benefits of precision forest inventory, what can be done and what is already done today on the market with high resolution data, inventory data, and the presentation from Maurice Fallon, the third presentation about using walking robots and drones to build accurate 3D forest models was in the same direction. So using new digital devices to gather data and information to have accurate inventory data and to come up with models with decision support and to see where the way is going to. And once we have this digital workflow, and of course, the machines can operate much more precisely, as we have learned in a very nice presentation of Pedro La Hera about machine data, the generation and use in the era of autonomous machines. And what he has presented is like 20 years of development, so we can get an idea of where we are today and where the work will be in the next I don't know, 5 to 10 years maybe. And so you can have an idea that we are really right within the frame of digitalization. And what Arnaldo has presented in the last presentation was really a nice, for me at least, it was a nice outlook about his work in the combinatorial optimization and in the quantum computer. And I think this is something where all of us need to get more into contact with. So thanks very much for giving us the insights in your work. And I would also like to use the opportunity to announce the second webinar, which is in 1 week from now. So that is Thursday, April 20. Yeah, I think this is exactly what Angelo is just writing into the chat as well. So next Thursday, we will have another 90 minutes webinar starting at 8 a.m. Central European Summer Time, or which is 1 p.m. VIB or 3:30 ACDT. And there we're going to hear something about the digital wood trade project at Stora Enso from Markus Wichert. We will learn about the utilization of standardized machine data from John Arlinger. We will learn about Forestry 4.0 and the digital twin from Michel Balasso. And the last speaker will be Mauricio Acuna, and he will talk about wood supply chain, automation solutions, opportunities, and challenges. And again, Raffaele Cavalli from the IUFRO office holder will be here, and Angelo and myself. And having said this, I would like to close this webinar and thank you for all your contributions and questions in the chat and for joining us. Have a nice day. Thank you.